Hi, my name is Ryan Hamilton. I'm the Elevation Product Manager at Maxar. Today, I just want to take a brief amount of time to discuss the Maxar 3D products. So I'll start just with an introduction of who Maxar is, integrated capabilities that connect Earth and space. Maxar is a trusted partner and innovator in Earth intelligence and space infrastructure. We make global change visible, information actionable, and space accessible. So, in a nutshell, what this means is we build and operate our own spacecraft that do a variety of things. But one of the primary things that we do is Earth observation. As a company, we're a medium sized company with about 4,000 employees in about 20 locations globally. But within that sector of space infrastructure and Earth observation, we really are the industry leader. Our satellites have the highest resolution commercially available, and we've got customers in over 70 countries with over 170 resellers. We have a broad footprint across a variety of commercial use cases, including telecommunications, automotive, sustainable development, technology and location based services, energy, marine, agriculture, and forestry. So, where does all this data come from? Well, our current constellation is the Worldview constellation, including GeoEye 1, and they're taking imagery constantly over the Earth, about 3 million square kilometers of the Earth's surface every day. And when you combine that with the legacy Iconos, QuickBird, and Worldview 4, our image archive is over 110 terabyte petabytes, excuse me, of imagery globally. This is a huge amount of imagery. And the importance of this for the 3D products is critical, and I'll get into that in a bit more detail. Exciting news for us is the idea that here in 2021, we will be launching the Legion constellation. This will add 6 new satellites to our current constellation. And one of the key pieces of this is that it will increase our capacity of high resolution 30 centimeter imagery by 3x our current capacity. So where we're currently doing 3 million square kilometers of the Earth's surface a day, about the equivalent of the country of India, we're going to be able to do 3 times that, which is very exciting for us. So for today's presentation, I really want to focus on the Maxar 3D and elevation products. And to start, it's best that we kind of give a little bit of a history lesson here and where this technology came from. Back in 2015, Maxar, who was then called Digital Globe, formed a joint venture with Saab and developed a company called Vricon. So Saab's input to Vricon was the IP for multi-view photogrammetry that's able to take a deep stack of imagery and produce 3D from those images, while Digital Globe, or Maxar's contribution, was the image archive library that I mentioned earlier. Fast forward to last year, about this time, Maxar fully acquired Vricon. So now Vricon is part of Maxar. So you'll hear me reference Maxar 3D as well as Vricon. Just keep in mind that Maxar 3D is the Vricon legacy technology as it's been integrated into Maxar. So what is this technology? Well, we're taking the image archives and building high resolution 3D that's very accurate, a 3-meter SE90, spherical error 90. So that's the LE and the CE in a spherical form for the accuracy globally without the use of GCPs. And we're doing this by using what's called multi-view stereo photogrammetry. This process is immensely scalable. It has to be, as we're trying to build the entire globe in the next couple of years in this high resolution 3D. And it's fully automated. The process is basically tapping into the Maxar library, pulling the images it needs and running the process all in an automated fashion and producing many of these derivative products that I'll talk about later, all automated. Portability. So in order to have this much data, we need to have the data in a very light format where it doesn't take up a lot of space. And accessibility in that we will be able to serve this data through APIs to customers that are looking for subscription-based services, again, with global coverage of these products. So I want to dump just a little bit of information on how these products are built. It's a very complex process, but I'll try and summarize it here quickly. Um, First is the global coverage from our satellite constellations. So the idea that the worldview constellations have been continuously collecting this imagery, and as Legion comes online, we'll have even more imagery coming into the pipeline. So the process is using the most current global coverage possible of all these images, um, and doing something different than traditional stereo. So with traditional stereo, where you may have a target that the satellite captures as it's approaching and then looks back on as it passes, multi-view photogrammetry utilizes the archive and utilizes all the different look angles of the satellites over that target area over a span of time. So as you can see in the image below with those green rays, those are actually the collection rays of the satellite over the city of San Francisco. And those are all the input images that are used within the process of multi-view photogrammetry over the building of that city. So then you move to step 2, and the actual production process happens. This is the idea of taking all those images from all those different look angles, and using those different look angles means that instead of having occlusion and areas that aren't being seen by the satellites, you're able to see into these urban corridors and areas that traditional stereo might have problem seeing. You're getting all that information, you're putting it together on a pixel by pixel basis. So when you do pixel by pixel matching, semi-global matching, dense pixel matching, you're taking this image stack and aligning it per pixel with every corresponding image. So instead of correlation of maybe a couple visible points in each image, you're actually looking at a couple billion points on each image and multiplying that by a stack of, say, 20 to 30 images over a target area. This is a very heavy compute process to build this 3D surface. But what you're doing is you're utilizing that true native resolution of the input imagery to build a very high fidelity 3D model. The other advantage of the multi-view photogrammetric process is the idea that as you align all these different images from the different satellites from different collection times, each one of those images have their own sort of native pointing accuracy errors. They're not perfectly positioned on the Earth's surface, but when you combine them together on a pixel by pixel basis, you're averaging out all the errors of all the images, and you end up with this highly precise 3-meter accuracy globally without the use of GCPs, which is actually, in comparison to Maxar's core image products, a higher positional accuracy than we can achieve just by the satellites alone. So as we move to step 3, this is really the output product. This is the true textured 3D surface, and it's the core product of this process. This product is a representation of not only the heights and terrain features of the Earth's surface, but also the exact texture and facades of those features, with every pixel placed in its precise location. We use this core 3D surface product to then build what you see at step 4, the derivative products, which could be traditional elevation products like DSM, DTM, point clouds, 3D vectors, classifications, orthos. So in summary, there's the 3D surface product, which is the core product, the 3D surface mesh. And from that, we're able to derive the elevation products like DSM, DTM, the ortho, true ortho, which is a nadir view of that 3D model, the point cloud, which is a point cloud representation of the 3D mesh, land use, land cover, or classification, and 3D buildings, which are vector representations of the buildings and vegetation features on the surface of the Earth. Just deeper dive into these products. Here's a view of the core product, the 3D surface model. And as you can see, it's very different from a traditional 3D product that maybe has an image drape on an elevation model where the building sides would be smeared. Or if you were to take off nadir images and try and cut them and paste them on the sides of the building where they might not have a true representation. With the 3D surface model, every pixel is in its exact location. It really is a true 3D representation of the surface of the Earth. From that, we can, of course, derive the more traditional elevation products like a DSM, which could be delivered in more compatible GIS formats like a GeoTIFF, for example. I already mentioned the true ortho being basically a simulated image where we've taken that 3D surface mesh, turned it to a nadir view, and then captured it. And so the advantage of this product is that when you look at high rise buildings and dense metro areas, you're not going to have occlusion or building lean. You're going to have a direct nadir view of all those features. We can utilize the NDVI process in the building of the 3D surface to include information about the classification of the features that are being built. So we understand where the vegetation is, we understand where water is, we understand where roads are, where buildings are, um, and utilize all that classification to help determine which each feature in the 3D model is classified as. Using that classification, we can then utilize automated processes to scrape the digital surface model to a bare earth terrain model, a DTM, which is applicable for lots of use cases where we're talking about the measurement of earth movement for planning and engineering, or hydrologic modeling and understanding flood models. These DTM products are important for that type of use. And then the final product I wanted to touch on was the vector buildings and vegetation. Um, this is the idea of actually utilizing those classifications, creating a vector of those classifications, and then extruding the heights from the digital surface model to those vectors. So instead of a raster model where you have a single surface that has some interpolation as the vertical surfaces meet the horizontal, with a vector model like this, you actually have a database where each feature can be attributed independently. And as the vectors intersect with the horizontal terrain features, there is no interpolation. As you zoom in on this product, it maintains crisp, clean edges and corners. This is an important product for the telecommunication use space. We have telecommunication customers that are using these 3D vector products right now to plan 5G networks. And they utilize these 3D models for simulations that show how the placement of their antennas is going to actually lead to enhanced coverage over their network areas. So a critical piece of this whole build process is the idea that the core 3D surface product is the product that all the other products are derived from. By doing that, it enables perfect co-registration of all those layers. So as we talk about classification or 3D vectors or DSM, when you overlay those products together, they are perfectly aligned. The classification will have a pixel to pixel match to the 3D vector lines, for instance. This is critically important for not only human interaction with the data sets, because it's all aligned as you turn between data layer and data layer, but when we start talking about machine learning and AI, the idea that we can provide data layers that are perfectly co-registered enable those machine learning algorithms to better process and understand what they're looking at without having to do any sort of alignments of various data sets. So as we talk of use cases for these products, well, obviously for elevation, when we talk about natural resources, exploration and resource extraction, having the elevation information is critical. Lithology studies to understand the basic subsurface features and how those are being identified on surface faults and features. As well as with resource extraction, understanding volumetric calculations, understanding planning for well pad, cut fill operations, things like that. Mining is a sector that really uses a lot of our elevation products. Another one is telecommunications. Like I mentioned before, the 3D vector products being used for RF planning. Also, the 3D surface model, or the DSM, for line of sight calculations, where wireless broadband providers are trying to understand from a tower location which customers can they service and which customers may not be serviceable because of terrain or feature obstructions. One of the criticisms of a multi-view photogrammetric process is the idea that it's not a set collection date. Because we're utilizing the image archive, we're having to do an amalgamation of different image inputs to build the 3D product. So one of our solutions for this is really the combination of the Vricon technology with Maxar has enabled us to really enhance the portfolio, where we can use the metadata of all the image inputs to understand the exact build vintage of the product, the 3D surface model. So we can understand, based off all the input images, what the actual output, what date that output represents in time of the features that were on the ground at that time. We can then co-reference that to what's called our persistent change monitoring um, observations, where we have been for years now monitoring change in the image databases to understand over time where persistent changes happen, meaning not just changes of traffic on highways or fields being plowed, but real persistent change that shows up pre-change as a series of images where it's not existent, and then post-change, it's continuously existent in that series of images. By classifying things with this PCM process, we can then utilize the vintage map of the Vricon data to understand post-vintage production. What changes have happened? How much change has happened in that area? And for customers, this can give them assurance of how the currency of the Vricon data will affect their use cases. But for Maxar, it really is a roadmap to where our update planning is going to happen as we build out the globe in 3D. Where are the places that we need to update the 3D surface mesh so that we have the most current and usable product globally available? So I think there's two pieces that I really want to emphasize with the 3D products from Maxar. First is the idea of a global database of 3D products, the 3D surface mesh, the elevation products, the true ortho, the classification, the 3D vector products. This will be a new paradigm in geodata globally. To have these products at a 50 centimeter resolution with a sub 3 meter accuracy is something that the geodata industry really has never had access to on a global basis. So the data in and of itself is an amazing thing, but the utilization of the 3D mesh as a global template or a global datum is another piece of the story that I think may get overlooked because of the data, but is really a critical part of what the whole Maxar 3D story is. The idea of precision 3D registration, P3DR, is the idea that we can utilize the 3D mesh to do pixel by pixel co-registration with imagery, full motion video, or high resolution 3D models, and take these very high relative accuracy products that may not have good positional accuracy or absolute accuracy, and positionally correct them based on our global 3D skin. So it's key to remember that when these type of products are collected, they may have a very high accuracy and fidelity, but if they are not co-registered to a database, they might not be as usable. When we talk again about machine learning and the idea that if you've got algorithms that are supposed to be tracking vehicles on a certain road, but every time you get a video feed of that road going into the algorithm, the road's in a different place, it becomes difficult for those algorithms to properly do what they're supposed to do. With a consistent global datum that all these images and live video feeds are tying to, it makes that alignment problem go away. So that's really a key piece of what the P3DR technology is enabling. And it's not just for imagery and video. The idea that high resolution 3D models could be collected from platforms like drones or other aerial platforms. Those two, again, will have a very high relative accuracy, but may not have the positional accuracy that's needed. As you can see in the original up top, that road on the far end, the western end of that 3D model, it's not aligned. And you can see post registration with the P3DR tool that it's got perfect alignment. So really, the key piece and the key takeaway on this is not that it's a one-off, hey, every time that an image is collected, I can run it with P3DR. But the idea with Maxar and our customers as well is that global data sets with this 3D skin can now start to have a consistent base to tie to. With Maxar, as we collect our imagery and reproduce our mosaics, having this technology and this global reference is critically important. As we look at small sat competitors and others out there that are collecting Earth observation information, having the same data set to tie it to gives you a uniformed position for all these inputs that you're using. So useful in both internal and external technologies. So I just want to show kind of some examples here, and this is sort of close to my heart as I was a digitizer long time ago. But the idea that when we would do heads-up digitizing of a city, every time a new image came in, there was a problem of, do we tie that to the existing imagery, or do we need to now shift all our old collections to match this new imagery? Because we would be digitizing road center lines and things like that. As you can see here, as it runs through this example, this is 20 years of imagery, 20 years of automated feature extractions. And there is perfect alignment of these road center lines as the road network grows year by year. So instead of having to go back and try and tie these lines together, figure out where to shift everything, it's already inherently there because the input imagery that's been used to derive these automated feature extractions is already aligned. If I zoom in a bit closer here, you can see this is an actual example where in 2010, this area did not have a lot of roads. And then as more and more development happened in 2020, there's a lot of roads. And this process was collecting each year, collecting the roads to try and map the area. And you can see as all those road vectors have been overlaid, there's very good correlation over 10 years of imagery of all those different vector lines. So again, this idea of a global sort of datum. That's a strong word to use, but the idea really is that there's a uniformed data set that all input data could be tied to is really one of the key pieces of this Maxar 3D project and the building of the globe in 3D. So I'd like to stop here and open it up for questions and see if there's any discussion topics that we can dive into a little bit more deeply. Thanks so much.
Wow, thanks, Ryan. That was a pretty amazing presentation. It was a really good presentation, but it was also pretty amazing to see this stuff that Maxar is working on and really exciting. I also want to thank Maxar as a gold sponsor for this conference and for your, giving us your time and everything that you had to share. I'm going to go straight into the questions because I'm sure we have a lot of interesting and exciting questions and people want to know more. I'm going to start with a question here from Jeff Zeiss. He'd like to know, would this 3D model be practical for engineering and construction firms to look at different alignments to estimate how much dirt has to be moved away for a new highway or railway?
Well, first off, thanks a bunch, David. Really appreciate it. And thanks for having me. I appreciate the time, get to talk about this stuff. So happy to be here. As far as that question goes, yes, for preliminary engineering, we see these elevation products as hugely helpful for understanding, if there's a pipeline, is it better to go around the hill or over the hill for highways and things? What's the cut fill going to be? The one piece I want to emphasize, though, is that temporal component, where with a LiDAR collection or maybe even an aerial photogrammetric collection, you will have a collection date. With multi-view photogrammetry, we're going to give you an estimated date of when the features in the 3D model represent the features that were on the ground based off the average of that image stack. So if it is something that is critically important that you understand change from 1 month to the next, I might recommend a traditional stereo product for something like that, where we could do a tasking collect. If it's all right to have those amalgamated dates, because it's an area that the terrain may not have changed in quite some time, then absolutely, for those engineering projects, it would work great.
Okay. No, that's great. And maybe just a kind of follow-up question from Jeff again. Can you derive cost and classify vegetation and calculate tree heights for vegetation pruning scheduling?
Yes, so we can do the vegetation height estimates in a comparison of, in the areas that we've classified the vegetation, we'll do a differential between the digital surface model, the first return model, and the DTM, the digital terrain model, the bare earth. And we can get those heights from that. And the beauty with the multi-view photogrammetry in comparison to other photogrammetric methods is that we do get foliage representation much better than we do with traditional stereo, for instance, just in that there's all these image inputs being used to calculate the tree height. However, again, it goes back to that temporal currency. So if you're trying to do encroachment estimates on power lines or something like that, we won't have specific dates of when those trees were encroaching into that area. It's going to be, again, an amalgamation of dates. So you can't be reliant on it to sort of schedule pruning or things like that.
Yeah. Okay. No, that's great. And I think, for me, when I look at the evolution of spatial data and how, you described that amalgamated database, there's a question here from Dennis that I think is really, it's the point. And like, who needs this data? And is there a technology race going on worldwide to work on this, or is there collaboration? Because, it could be powerful.
Yeah, so the interesting thing, and this is why the joint venture back in 2015 between the defense company Saab and at the time Digital Globe made so much sense, in that we really, as Maxar, are the only ones that have this multi-layered coverage of the globe in this high resolution imagery. So that fuel to sort of power this engine of multi-view photogrammetry is really unique to Maxar, in that we're the only ones that can produce a product of this fidelity with a global coverage. Now, of course, there's competitors out there that can do areas and can do parts of the globe, but to really build the entire globe is a unique capability of Maxar. We do have other partners that we collaborate to produce 3D and elevation products, but when it comes to the globe, it's now internal to Maxar with this Vricon technology. And to that first part of the question, traditional elevation use cases, that we could list a whole bunch of what they would be using this data for. The engineering example that was brought up earlier, and telecommunications was a use case, flood and hazard mitigation, things like that. It's opening up a whole lot of new use cases for a global data set, because we just have never had this high of resolution and high of accuracy from a global data set. There's SRTM, there's World Dem from Airbus, there's the AW3D product, but they're all much lower resolution and lower accuracy than this, where you're almost getting LiDAR-like quality on a global scale. And then the 3D component in these new emerging technologies, where there's lots of visualization and and sort of viz sim components to those technologies. We're seeing a lot of traction in the marketplace because of that photorealism that the 3D surface brings.
And now that you touched on that point of accuracy, just I had a quick question about if you added GCPs, could they be used to further improve that accuracy on or?
Yeah, so we can add ground control points as sort of a custom based production process. It's not part of the standard process. The process was really what we wanted to do when we enabled the initial workflow was to allow global consistency. And there's just some areas in the world that you cannot get ground control points. So we wanted to make sure the product specification was uniformed across all regions of the world. So we developed it without the use of ground control points. And frankly, the use of ground control points only adds a very incremental increase in the accuracy. It's very different than traditional stereo where they're reliant on ground control points to meet your accuracy specification.
Yeah.
With this process, it's a fractional improvement, but it can be done at a custom basis.
Okay, and maybe just only have time for a couple more questions. There's a couple of interesting ones here tied to that process. There's one from Irene Chang about is there a generic trained machine learning model for all cities, or is there a unique trained model for each city for 3D construction? And does that transfer learning come in here, or?
That's a very interesting question, actually, and you've touched on one of the key pieces of this technology is that the machine learning, the AI that's doing the processing is morphology dependent. Not so much cities, but the idea of is this the high desert plains? Is this agriculture? Is this urban? Is this snow and ice? All those different morphologies, we have different algorithms that help with the dense pixel matching or semi-global matching process. So the teams that visually inspect each output tile are looking to make sure that the right morphologies in the algorithm were chosen. And so there is, short answer is yes, we do use different technology or different algorithms for different areas.
Okay, and I guess it's kind of follow-up question to that from Irene. Triangulation of 3D mesh reconstruction is very computationally expensive, and I suppose it's processed offline. How often does Maxar update the 3D textured mesh models in order to accommodate these dynamic changes on the ground?
It's a great question too. So the goal right now for Maxar is to complete the global 3D build. So producing as much data as we can. And there was a piece of my presentation where I talked about the utilization of the vintage map that basically shows what we consider to be the representative date of that data set based off the average image date in the image stack compared to what we call persistent change monitoring. And that process of comparing those to find where there's areas where we have older vintage of the 3D build and areas with high amounts of change are the inputs for the update strategy once the globe is filled. But for now, the focus is getting this global product, this global skin of 3D built as rapidly as possible, and then going back and doing the update programs. Of course, for opportunities that require higher currency or better currency, we can do custom builds on that. But short answer is we have tools to find those older areas and we'll update accordingly.
Okay, I have time for one last question. John Roos asks, Ryan, you guys probably know each other. Ryan, you discussed your surface 3D capabilities. Can you touch on your bathymetric capabilities with Maxar imagery?
Oh yeah, so with the Maxar 3D Vricon process, we are doing optical photogrammetry. So we're not actually doing any bathymetric elevations in that model. We do have other partners. T-Carta is our partner that does a signal noise or a signal strength evaluation to do nearshore bathymetric models. So we can utilize the signal returns from our imagery to understand depths. And we can build those bathymetric models in 30 meters or less depth of water, and get very high precision bathymetric models that then in turn can be tied to these surface 3D models. So you have a complete, sub ocean floor model all the way to the terrain, and how those transitions happen.
Cool. Ryan, I don't know if I try to ask all the remaining questions, I'm going to be speed reading, and I don't think everybody's going to get it very clearly. We have another talk scheduled in about 10 minutes, and we need a break to transition through to that. So I'm sure your details are available to all our attendees. It was such an exciting talk. I have lots more questions I'd like to ask you myself as well. And so thank you very much, Ryan, for your time, and thanks to the Maxar family for supporting the GeoIgnite conference yet again. Yeah.
Absolutely. Thank you, David. Really happy to be here.